And to present an overview of Starches is Dr. Yongfeng Ai. And before we proceed further, I would like to introduce myself. I'm Puba Ganeshan, the principal scientist at the Food Center with the Fermentation and Bioengineering program. But before we get to the seminar or webinar, I would like to just go through it. For those of you who are not familiar with the Food Center, just a few slides about what we do here. The Food Center has been in existence for over 25 years, primarily providing innovation to the agri-food sector. Located in Saskatchewan, it has a strong focus on local crop and meat utilization, plant-based foods and ingredients. It has generally over 60 full-time employees with diverse backgrounds, expertise, and skills. And Food Center has supported over 520 clients over the years and developed over 1,100 products. Its role in industry is primarily to expand and drive innovation, utilizing Saskatchewan agri-food products and processes, and to help entrepreneurial support across the markets, and also to provide risk reduction in capital for entrepreneurs, besides developing the ecosystem to support commercialization of new technology, research, and development. Primarily supporting clients in North America, Canada, US, South America. We also service clients across the globe in Europe, Asia, Africa, and with a constantly increasing number of clients that we are constantly being sought after. We have 3 facilities currently, one on campus and one at the agri-food in the West Industrial side of Saskatoon, and a 3rd facility that has been just up and running. The 2 facilities are equipped to manufacture a wide variety of food products, including meat alternatives, dairy, non-dairy, fruit and vegetables, and other condiments and snacks. We are organic, ASAP certified, BRC halal, FDA, and CFIA inspected. And we offer commercial manufacturing, daily rentals, long-term incubation suites as well. The latest facility, the Fermentation and Bioengineering Services, is just starting and focused on submerged and solid-state fermentation systems, as well as a suite of downstream processing equipment for ingredient processing as well. Without any further delay, I welcome our guest speaker today, Dr. Yongfeng Ai. Dr. Yongfeng is an associate professor and the Saskatchewan Ministry of Agriculture Endowed Research Chair in Carbohydrate Quality and Utilization in the Department of Food and Bioproduct Sciences at the University of Saskatchewan. The primary goal of his carbohydrate chemistry and utilization program is to promote value-added utilization of carbohydrates in foods, feeds, and bioproducts. His research areas include carbohydrate chemistry and nutrition, value-added processing of cereals and pulses, and biomaterials. Dr. Ai obtained his Bachelor of Engineering degree in Food Science and Engineering from China Agricultural University in 2008, and his PhD in Food Science and Technology from Iowa State University in 2013. He has published over 60 refereed journal articles and 7 book chapters, and delivered more than 30 invited presentations at national and international conferences, workshops, and webinars. Dr. Ai currently serves as a technical program chair of the US Starch Roundtable and chair of the Carbohydrate Division and Cereals and Grains Association. He's an active member of Institute of Food Technologists and Canadian Institute of Food Science and Technology. Welcome, Dr. Ai. And before we proceed to Dr. Ai's presentation, I remind our audience they can type in all their questions in the chat box, and those questions will be answered at the end of the webinar. Dr. Ai, it's all yours.
Thank you, Puba, for the nice introduction. Can you help me confirm if you can hear me and see my slides?
I can hear you, Yongfeng, and
How about my slides?
yes, it's on now.
Okay, great. Yeah, I also see it. Thank you for the introduction. And before I start, I would like to thank Food Center for giving me this great opportunity to share our research with audience from different parts of the world. I received the registration report yesterday. We have friends from more than 20 countries who are interested in this topic join us today. It's really great to have all of you guys here to join in the discussion. I moved to Canada from Michigan State University to start a new program in 2016. Value-added processing of pulses and also the utilization of pulse starch is one of the main focus of our program. In today's webinar, I'm going to share with you what we have learned in the past 8 years. Here is the outline of my talk today. In the introduction, I will share with you what is starch and the techniques we use to study starch. Also, because there is a continuous interest in resistant starch, I'm going to use one slide to share with you starch digestion and resistant starch. Then after that, I will share with you some information regarding post-processing and also why we want to find new ways to utilize the starch as the main co-product from the processing of pulses. After the background information, I will share with you the first paper we published in our group. In the paper, we try to compare different pulse starches with the commercial starches, and then to see their different structural features, functional property, and also digestibility. For the main part of my presentation today, I'm going to share with you one research program. We call it the Strategic Research Initiative Program. For this program, we receive the funding from our provincial and also federal governments. For that year, the SI program, the topic of the research was on post-starch utilization. And we have different research themes within the program. And today I'm going to cover the fractionation of starch and protein in pulses, the food ingredient innovation, mainly focused on the starch side, and also some very interesting research on how we use a different new method to convert starch into biomaterial and also biomedical material. So what is a starch? Starch is actually a biopolymer of a D-glucopyranose. And starch, as we already learned from food chemistry course, it's mainly consists of amylose and amylopectin. Amylose is essentially a linear molecules, as you can see here, and amylopectin is a highly branched molecules, as you can see. The branch chain is connected by alpha 1,4 linkages, but it has the alpha 1,6 branch linkage, as you can see here. So for the amylopectin, it's known as has about 4 to 5% alpha 1,6 branch linkage. So it's a highly branched molecule. Amylose content of the starch we can find in nature. Usually have amylose content range from 0 to 85%. 0, we are usually talking about waxy starch. Many crop have this like a waxy variety. But unfortunately, as far as I know, for pulses we grow in the world, we don't have a waxy variety. The lowest amylose content I've seen for pulse starch is about 13%. And we also have the some high amylose line. The highest line we have seen is about 85%. And then for these lines, actually, the high amylose starch is commercially available. why we are so interested in amylose content? Because the amylose content will affect the thermal property, pasting property, gelling ability, and enzymatic digestion of starch. And in today's talk, we are going to see how it will really affect the utilization of pore starch. Because when we talk about the processing, the chemistry of starch, there are many terminologies. And I would like to use this slide to share with you the different techniques we use to study the functional property of the starch. And also this will help us to cover some of the basic concepts which will facilitate our discussion. Starch in the nature are known to be present in a granular form. And then when we add it to water, it will absorb about 30% water. So because of that, the granule will start to swell. But this process is reversible. So which means if we try to remove the water without like provide very high temperature, just like a room temperature to allow it to dry, and actually we can have the starch granules go back to the original state. So it will shrink, and then basically we observe little change to the starch granule. But if we have the swollen starch granule and we have a sufficient amount of water, then we heat it. Now what happens is starch gelatinization. And actually we do this every day in our kitchen. So usually for the gelatinizing of the starch, we use a machine called differential scanning calorimeter. This is the most reliable machine we can use to study the starch gelatinization property. Once the starch is gelatinized and then we heat it and we continue to stir it, what we observe is the viscosity development. So usually this is known as a starch pasting property. And then to study the starch pasting property, the most commonly used machine is a rapid viscous analyzer, or as RVA. And also once in a while you will see in the literature, people also use a rheometer to study the pasting property of starch. And if once we obtain the starch paste, when we cool it down, some of the starch, not all the starch, but some of the starch, they can form very good gel. The difference between starch paste and the starch gel is starch paste can flow. It has a good fluidity. It cannot hold the shape, but starch gel cannot flow. It has a self-standing or self-supporting structure. And then you can more interpret this as, like, for example, like a jello. Even though jello is not made of starch, it's made of gelatin, but the starch gel has similar texture. I hope I make it clear the difference between starch paste and also starch gel. So for the starch paste, when we cool it down, some of them will form a gel. And when we heat it, and then with the stirring, actually the starch gel can also be transformed back to a starch paste. So this process most of the time is known as a reversible as well. So for the starch gel or starch paste, actually when we store it at a room temperature or at a 4 degrees Celsius in a refrigerator, the starch will go through a retrogradation process. So this is basically the functional property of the, like when we really try to use starch in food and other system. And one thing I just want to add is to determine to really study the starch gelling ability. One machine we can use is a texture analyzer. We can use it to determine the gel strength. And actually we use this method frequently in our publication. Recently, we also try to use a rheometer to monitor the whole gelling process. So this is the overview of the functional property of the starch. Also, there is an increasing interest in using starch to develop resistant starch, which will provide low glycemic benefits. Also, some of the resistant starch is accepted as a type of dietary fiber. So I would like to use this slide to share with you the digestion of a starch in our GI tract. So when we ingest the food containing starch, the digestible starch will hydrolyze by 6 enzymes in our GI tract, including salivary alpha amylase, pancreatic alpha amylase, glucoamylase, maltase, sucrase, and isomaltase. After hydrolyzing by the 6th enzyme, the digestible starch will be converted into glucose. And then glucose will be absorbed as a main energy source in our body. But for all the starchy food we consume, it always has a portion of a starch that cannot be digested, which is defined as a resistant starch. So resistant starch is a portion of a starch that escapes the digestion in our small intestine. And then resistant starch will be passed into our large intestine to be fermented by the gut microflora to produce short-chain fatty acid, including acetic, propionic, and butyric acid. And short-chain fatty acid are known to provide various health benefits to our colon. And some resistant starch actually can survive the fermentation in the large intestine. They can be present in the feces to increase our fecal bulk. That's also one of the health benefits resistant starch can provide. So this is about the digestion of starch in our GI tract and also the concept of a resistant starch. So with that being said, I would like to switch our gears to talk about the post-processing because our topic today covers the mainly cover the post starch. So pulses actually we mainly they are the crops in the legume family. We grow them mainly for the dry edible seeds. The most common pulses we grow in North America include pea, lentil, dry beans, chickpea, and faba bean. And in the past 20 years, increasing volume of the pulses, they are used for the processing to produce different food ingredients. I would like to use this slide to share with you how we can transform the whole pulse seed into different ingredient. So when we have the whole pulse seed, the first step usually we do is a dehulling. By dehulling, we will obtain the split pea, and then also we obtain the hull fiber. And actually, hull fiber is a very popular fiber in the food industry, also in the pet food industry, because we can add it to the different formulation to easily boost the fiber content in our food or pet food products. And also the split pea, they can be easily milled to produce a pea flour. And then pea flour has found very good use in bakery goods, in like extruded snack and many other products. If we want to further fractionate the starch and the protein, one method we can use is a fractionation, dry fractionation. And then for this method, usually we will start with a pea milling of the split pea, and then followed by L classification. So after the processing, we will obtain the starch-rich flour and also the protein-rich flour. Almost all the companies in our province in Saskatchewan, they use the dry fractionation to further extract the protein and also the starch. The second method we see in the industry is a wet fractionation. So for wet fractionation, we will use a different solvent to further separate the starch and protein. And then one of the advantage of this method is the high purity of the derived ingredients. So after the wet fractionation, we can obtain the isolated starch, which can be used to produce the glass noodles, which is a very popular product in East Asia. Unfortunately, the market in North America, we don't consume such a large volume of the glass noodles. And also, you can read find on the internet, isolated pulse starch can also be used to produce the gummy bear candies. The protein isolate is what people are looking for these days, right? And then the main reason is because we are interested in using the pea and other protein isolate to produce the plant-based meat analog, the beverages, and also the protein powder. So also after the isolation, we obtain the cell wall fiber. Cell wall fiber, sometimes in the industry, people also call it internal fiber. So actually, it's a fiber we obtain from the cell wall of the cotyledon. It's different from whole fiber. If you look at their functional property, they are not the same. They are two different types of fiber, and they have different applications in the food industry. So in addition to the two method, actually there's a method. Sometimes you can look at into the literature. People call it a hybrid method. So what we mean is, particularly for the starch-rich flour we obtain from the dry fractionation, actually we can use a wet method to further extract the protein and also to the starch. We can increase the purity. So we can really obtain the high purity of the protein and also isolated starch. So sometimes people call it a hybrid method. So actually in the past 3 years, we have one student, Oneli Makalab-Gamma. She worked on one project. We tried to use the wet extraction method to further separate the starch and the protein from air-classified starch pulse flour we obtained from Saskatchewan. And then we also look at the functional property of both the starch and protein in her thesis. Her thesis is actually publicly available. If you are interested, you can go to take a look. And then for this study, we try to control the flour to water ratio at 1:10. The extraction time is 1 hour. Then the two parameters we control include temperature and also pH. So for the temperature, we tried 25, 30, 40, and 50 degrees Celsius. For the pH, we try 8.5, 9.5, 10.5, and 11. So we have all the different combination of the condition, and then to see how the different conditions affect the purity and the yield of both starch and protein. Also, we look at the functional property. Actually, we through the the investigation of the different condition, we already identified the optimal condition to obtain the highest yield or highest purity. And also, another very interesting aspect of her thesis research is we observe the different condition can really affect the functional and nutritional property, both protein and the starch significantly. So if you are interested, you can go to take a look at her thesis. Because of time constraint, I'm not going to go into the detail of her thesis work. But I hope these two slides give you a good idea. When we start with a whole pea seed, how we can convert the seeds into different ingredients. And there are different methods can help us achieve the goal. But when we talk about processing of any crop we grow in any country, the first thing usually we need to look at is the chemical composition, right? So for the pea, lentil, and the faba beans, which are most commonly used for the value-added processing, and what we can see is for these different post crops, their starch content usually range from 40 to 50%. And then protein content range from about 21% to, like some of the faba bean may go to 33%. And then also they are a good source of dietary fiber. But the key information I want to share here is when we look at the starch content and also the protein content, the starch content is roughly twofold of that of protein, right? So what I learned from the industry when I started as a assistant professor at our university is when we produce 1 volume of the protein, no matter using a dry or wet method, usually we produce about 2 volumes, 2 to 3 volumes of the starch as a co-product. Okay, so with that being said, the one of the goal when I try to start a new program at our university, then one main research question is how can we generate the value from pore starch? So this include the starch-rich flour from dry fractionation, from air classification. In Saskatchewan, mainly you will find the starch co-product in this form, and it contains about 60 to 80% starch. But also this include isolated starch, which usually contain about 96% starch or even higher. So how can we really find good ways to utilize this main co-product from the extraction of post protein. So to answer this question, the first project we started when after I joined the university is we try to look to gain a more comprehensive understanding of post-starch. So in this paper, we try to compare the pea, lentil, and the faba bean starch and try to compare it with the different commercial starches. In the interest of time, I'm not going to go into the details of the paper, but some of the key findings I want to share with you. So when we compare the three post starches, we isolated from the L-classified starch-rich flour of the pea, lentil, faba bean. When we compare them with the waxy maize, normal maize, and tapioca starch, the post starches, they show high amylose content. Usually the post starch we work with in North America. Sometimes I also help some American companies to determine the amylose content of their post lines. Usually amylose content fit into this range, 38 to 41%. Sometimes maybe a little bit lower, like 35. So 35 to 41% is a good range. And then the other commercial starches, waxy maize, normal, and tapioca, they are the most common commercial starches you can find in the market. They has only about 1 to 31% amylose. Then post starch, they also have a higher retrogradation rate. We clearly present that in our paper. So retrogradation rate is a good or bad thing. It really depends on the application. If you use it as a thickener or stabilizer in soup or in yogurt or a similar product, retrogradation is usually considered as undesirable because it will lead to a phenomenon called stenosis, which means after storage for a while, you will observe the separation of the liquid from solid, which is usually considered as undesirable. But for some of the application, for example, for the preparation of the glass noodles or Chinese vermicelli, actually the high retrogradation is a good thing. It can help to set the structure more quickly. It can also provide the firm texture of the noodle product. And also, post starches, they have a very good gelling ability. So in order for you to better understand what I mean is I pick the pea starch gel and also tapioca starch paste here. They were prepared at the same starch concentration, 8% starch, and then they will cook using the same waste store for the same period of time. You can observe like a pea starch, it can hold the shape, it cannot flow with no fluidity, right? But the tapioca starch paste, it cannot hold the shape, and it can flow, it can give you very different texture. Right? The main reason we care about if a starch can or cannot form a gel is mainly because they can give you very different texture profile. If you eat this starch and then you eat a tapioca starch paste, they will give you very different texture properties, right? So actually the industry already utilized this unique property of the post starch for centuries, actually. For example, like the glass noodles, as I mentioned, you can see on the right-hand side, this is the glass noodle made out of the post starch. They have a clear, like a very good color and also very firm texture if you don't overcook it. Also in some regions in East Asia, and then people also use the pea starch to prepare the jelly type of appetizer or dessert. You can see here, this is the product. So it's similar to Jello, right? Like available in grocery store, and then it will give you very similar texture. But Jello is made of the gelatin, but this one you can make it out of 100% starch. But one thing I want to share with you is what I learned from local food producers in East Asia is most of the time the consumers, they have to eat it fresh. Because as I mentioned, post starches, they known to have a higher rate of retrogradation. If they don't consume it as a fresh, if you put it in refrigerator overnight, and second day when you take out the same food, and then you will see the separation of water at the bottom. And actually, when we work with post starch in our lab, we observe this frequently in the beginning because Sometimes when we want to do some analysis, we cannot finish all the sample, we put it in a fridge. Second day, you can see the recirculation and syneresis very obviously. And also, pulse starch has been used as a substitute for gelatin and also pectin in gummy confectionery, like you can see here, gummy bear candies. They are commercially available product made out of pulse starch, and also soft capsule share, as you can see here. And then definitely for this application, some modification has to be performed in order to optimize the performance of the different pulse starch in these products. So we cover the strong gelling ability of the different pulse starches. And also when we when we just analyze the digestibility of the starch in a raw granular form without cooking. So actually the pulse starches, they show a greater enzymatic resistance compared with the other three starches, except for tapioca starch. One of the reasons is because of the pulse starch, they have the C-type, the crystalline structure, and also they have a better like high amylose content, as I mentioned. Also, their internal granular structure is more homogeneous. They have a less porous structure. All these factors contribute to the greater enzymatic resistance of the pulse starch. So you may ask me, what's the significance of this? In Canada, actually a large portion of the pulse starch, particularly for the like starch-rich pulse flour, goes into the feed industry. Sometimes there is a minimal thermal processing. Now, actually now the resistant starch present in the pulse starch will be important for the nutritional aspect of the starch in animal feed application. But when we talk about the human food application, if we have an isolated starch, after we cook it, actually most of the time the starch will show very similar digestibility as compared to cooked waxy maize, normal maize, and tapioca starch. And the more we work with the starch, the more we realize the low glycemic benefits of pulses is most of the time is actually not from the starch itself. Because when we use a pea and pulses and also the derived ingredient, most of the time we will cook them, right? So once we gelatinize the starch, actually the digestibility is similar. So one of the main factors contributing to the low glycemic benefits of pulses is actually the interaction between starch and protein and fiber. So when we have the compact structure from the cotyledon, the protein and the fiber, they will play a role as a physical barrier to delay the starch digestion. And definitely, if you just compare the starch content of a pulses with cereal, pulses in nature, they have a lower starch content, right? So when you consume the same amount of the pulse grains and then cereal grains, because of the lower starch intake, you will observe a lower glycemic index as well. So I think for this is a totally different topic, but I'm going to present you with one study. We just use water to modify starch, and actually we were able to reduce the glycemic response of the starch in human. It's also in cooked form. So it's a study we just published. It was accepted last week. So I'm going to share more with you about the greater enzymatic resistance pulse starch in a raw granular form. They are important for feed application. Then one last note I want to share with the audience is when we look at the pea, lentil, and the faba bean, at least for those samples we obtained from different sources in North America, generally these pulse starches, they show similar structural features and also functional attributes. Why this is important? So my understanding is when we try to perform research on the value-added utilization of pulse starch, actually, if we find a way that can be good for pea, I'm pretty sure it will also be good for lentil and faba bean. So which means because they have a similar structural features and also the functional attributes, if one method can work for any of the pulse crop, it should be good for the other starches as well. I'm mainly talking about the pea, lentil, faba bean. For some of the like a minor pulse crop, I think we need to do more research. But at least based on our study, these are some of the unique features of the pulse starches I want to share with the audience. So with all the information, I would like to go to the main part of my presentation today. It's mainly focused on the research we have performed within the Strategic Research Initiative Program, SI program. And for that particular year, we received the funding in 2020. For that particular year, the program focused on post-starch utilization. And then for this program, it's managed by our provincial government. We received the funding from our provincial government and also federal government under the Sustainable Canadian Agriculture Partnership. So for this program, we try to we started research with a whole seed of the different market classes of this crop. And then the first step we do is a fractionation. Actually, we tried, we did the dry fractionation, like using L classification. We also did the wet fractionation. So after the fractionation, we can have the starch-rich flour and also the isolated starch, as I mentioned before. And then after that, the second research theme, we focus on food ingredient innovation. And also our collaborators try to use a fermentation to convert the starch-rich flour into like a fermented protein and also into the symbiotic, which is a composite of the both prebiotic and the probiotic. Also, we try to convert the either starch-rich flour or isolated starch into biomaterial, and we mainly use isolated starch to prepare the biomedical materials. So in the this program, we have 9 research labs in Western Canada to work collectively to achieve the goals in different research pillars. We have breeders, Dr. Tom Workington and Boyami Tarrant, and then they provide the premium quality seed of the different market classes for our research. So we can use them for different fractionation, and we can try to isolate the starch for the downstream processing. Also, we have a food scientist and also microbiologist to mainly look at the food ingredient innovation and also bioconversion, including myself, Dr. Mike Nicholson, Darren Cooper, and Tak Tanaka. We are in the same department. And also we have an animal nutritionist. They use the like the pig as a good model to evaluate the glycemic response of the different pulse-based ingredient, and also the look at the fermentation of a resistant starch from pulses. So we have a Dr. Denise Bolio and also Dr. Daniel Columbus. Also, we have 2 engineers, Dr. Vishnu Acharya and Dr. Malcolm Xin. They mainly look at the biomaterial and the biomedical materials. So we worked together in the past 3 years, and we have made a very good progress in the different research objectives. I'm going to highlight the most exciting findings from the collaboration. So for the first one is the fractionation, and then for this research theme, I will share with you some of the very interesting findings. We try to use a pre-treatment of the seeds and then try to see if we can further enhance their performance during air classification. So for this project, we start with a pea, faba bean, and also lentil. And then the pre-treatment we tried include the germination and the soaking in salts. And then after that, the seeds will be dried, and then they will be pin-milled and then go through air classification. So we will obtain the starch-rich stream and also the protein-rich stream. And then because most of the time people are interested in the protein-rich stream, right? So I will mainly focus on the results on on this side. So this is a slide to show the protein retention. So for the protein retention, we mean how much protein we can retain in the protein-rich stream. So if we say 100 grams of the protein in the original seed, how much we can retain in the starch, in the protein-rich stream. So what we observe is, if you look at both the pea and the faba bean, and then for the control without any pre-treatment, so this is just a native seed. For the pea, we obtain about 62% the protein retention in the protein-rich stream. But for the faba bean, we obtain about 71%. Most exciting thing is actually after the pre-treatment, we can significantly increase the protein retention in the protein-rich stream. For example, for the P, we can increase it by 6.6%, so the retention can reach about 68%. And then the faba bean can jump by even higher number, by 18%. So we can recover almost 88% of the protein in original seed. So this is something significant, and actually we filed a PCT for patent application already. So after the student obtained the results, we want to answer the question, what caused this effect, right? So one factor we're thinking is the most important is because this treatment will really disrupt the protein and the fiber matrix in the seed. So what do I mean? So if you look at the raw seed, like the control, you can see actually the starch granules, they are embedded in the compact protein and the fiber matrix, as you can see here. But after this treatment, you can see actually the treatment were able to disrupt the protein and the fiber matrix. Now the starch granules, they are no longer compactly entrapped in the protein and fiber matrix. So in the downstream processing, we will obtain a better separation of the starch and protein. That's the reason we can recover more of the protein in the protein-rich stream using the L classification. And then we observe similar thing for the faba bean. You can see in the raw seed, the starch granules, they are embedded in the matrix, right? But after the pre-treatment, you can see actually now the starch granules, they are released from this kind of structure. So during the P milding and during the L classification, they can be better separated. And another study also fit into this theme is into the thing of a fractionation is the study I already mentioned. So we try to vary the wet extraction method by using different temperature, by using different pH, and then we try to further purify the protein and also starch from the starch-rich flour. And as I mentioned, we not only just obtain very good yields, very good purity, but also the functional property of the starch and protein can be significantly altered by the different conditions. So when I was discussing the thesis work with O'Neilly, we were thinking maybe even just simply change the modification method, we can modify starch and the protein. That's just one thing we observe very significant. Not just the yield, but also we can basically manipulate the functional and nutritional property of the both components in pulse grains. And then the second pillar, where, as I mentioned, is a food ingredient innovation. I'm going to share with you a clean label and a physical method we developed to modify pea starch. And then for this modification, the only reagent we add is water. So we start with a native pea starch and we add water, and then we do a cold extrusion. What do I mean by cold extrusion? So we use a high moisture level, 37.5%. We only use a conveying screw. We control the barrel temperature below 70 degrees Celsius. So with this kind of condition, the goal we want to really achieve is we want to develop some starch dough with minimal cooking. So after that, we place the extruded on an aluminum tray, and we place it in oven at 130 degrees Celsius for 1 hour. This step is the key, because with the high temperature, it can provide two effects. One, it can provide a hydrothermal effect. Hydro is from the water, thermal is from the heat, right? This is one effect. And second, it can dry the sample right away. So after this treatment, and then we mill the sample to pass through 0.5 millimeter sieve, then we can obtain a modified pea starch. And the paper is actually already accepted by Carbohydrate Polymer last week. And then hopefully it will be publicly available soon. And after we modify the starch, the first property we look at is a pasting property, because it can give us a lot of information about the interactions between starch, the interactions between starch molecules, and also how this modification will change the granular structure of the starch. And then for the pasting property, we use two temperatures. One is a 95, one is a 120 degrees Celsius. So when we look at 95 degrees Celsius, compared with a native starch, which can develop a very good pasting curve, the modified starch actually show very low viscosity. So when we really look at the granular morphology, it's not difficult for us to understand why at a 95, it will show very low viscosity, because after the extrusion and also the heating, we destroy the granular structure. And also, we believe during this process, there is a significant level of starch damage. So with the loss of the granular structure and also the damaged starch, then the starch cannot develop the same level of the viscosity as a native starch. And we also analyze the pasting property at 120 degrees Celsius. What you can see is actually for the native starch at a higher temperature, the viscosity already start to decreasing. But for the modified starch, it's very different. When we cook it, this starch at 120, it actually develop high viscosity. So when we cool the paste at 50 degrees Celsius, what you can observe is actually the final viscosity is even higher than the native starch. It's about 1.7-fold of the native starch. So what does this set of data tell us? So this data suggests that the modification actually induce very strong molecular entanglement between the starch chains. Because of that, we need a higher temperature in order to allow the starch granules to develop the viscosity. And also because of they have such a strong molecular entanglement. It's a physical association. So you think about two polymer molecules, they associate with each other. Then when we try to cool it down, it can develop very high viscosity. So after we observe this set of data, we also hypothesize the strong molecular the entanglement may also lead to lower digestibility of the starch. So with that being said, actually we went ahead to perform a human feeding study. So for the human feeding trial, we actually cook 35 grams of either the native or the modified starch. We boil it in water until both of them were cooked. Then they will control at exactly the same amount of starch. Then after the cooking and after we cool the sample down, we fed the sample to 20 human subjects. So 20 human subjects for the native and 20 for the modified starch. So here is the results. And actually you can see our hypothesis was true. And the modified starch did show lower glycemic response than the native starch. So when we really calculate the incremental area under the plasma glucose curve, you can see we reduce the glycemic response by 22%. This is very significant because we believe this modification is very simple. The only reagent, as I mentioned, is water. And then because of the low glycemic response, we believe the starch can be used to prepare like low glycemic food to help the diabetic individuals and also the public in general to control the glycemic response. And also this starch have some very interesting functional property. For example, it can develop very good viscosity under harsh processing condition. So currently we are trying to refine this condition for different porous starches, and also we are evaluating the food application value of this modified starch. I need to go a little bit faster. For the period 4, we look at the biomaterials, and then for the biomaterials, because of, as I mentioned, porous starch, they can form very good gel, right? So we try to use this property to prepare biomaterials. So for this project, we add the P-starch, polyvinyl alcohol, PVA, which is another biopolymer. We add water and glycerol as a plasticizer. We also add the salt. And then we cook everything in a pot. And then after cooling, actually we obtain some very conductive hydrogel with very interesting feature. You can see this is the gel after we cool them down. It has a very good mechanical property. It's flexible and ductile. You can see we can twist it, and it also show very good strain by dynamic mechanical analysis in our lab. And it has a tensile strain of 291%. So which means when you stretch it, it will stretch to 4 times of the original strain, original length. And also because we add salt, to the formulation, and salt, they are known to suppress the freezing of water and other plasticizer, right? So what we try to do here is we want to freeze our hydrogel to see what will happen. So we have a P hydrogel, and then the P hydrogel with the salt. So the first thing we do is we have the gel, then we cool it down to minus 70 degrees Celsius. And then after that, we heat it again. This is a heating curve, okay? So what we observe is for the P hydrogel without salt, we observe the melting of the plasticizer. I don't believe it's just water. It's should be water and a glycerol. We can see the melting temperature is minus 19.7 degrees Celsius. But for the sample with the salt, the temperature is much lower. It's minus 34.7. So it's a 25 15 degrees Celsius lower, right? So which means the actually the salt, the presence of the salt suppress the freezing of the plasticizer. So why this is important? So we went ahead to look at the anti-freezing property of the P starch hydrogel. When we prepare the conductive hydrogel, we store at a minus 20 degrees Celsius. So right after we take it out, this hydrogel can still retain very good mechanical property. It is still very flexible, very ductile, and then you can still twist it. And the tensile strength only decrease from 291 to 255%. So which means even just after freezing for a few days, you can still stretch it, and then the gel can reach 3.5 times of the original length. So we are thinking to, because of these interesting properties, also it's a conductive gel. We are thinking to use it as a sensor for like a strain sensor, like to monitor our body movement. Also, we're interested in using it to develop the temperature sensor. And then also the PhD student Chen Yongzhu in our group, we try to use the starch gel to prepare biomaterial for nutraceutical application. So for this study, we start with a round P starch and also wrinkle P starch. Round P starch has about 39% amylose, and wrinkle P starch, which is known as a high amylose version of the P starch, it has about 71% amylose. So after we have the different starch, we cook them at the 3 different temperatures, 95, 120, and 140 degrees Celsius. What we can observe is the round P starch, the gel strength decrease as a function of a cooking temperature. But the wrinkle P starch, it cannot form a gel at 95 degrees Celsius, but at a higher temperature, it can give you a much stronger gel. So why they are so different? The round P starch, we believe the decrease in the gel strength at a higher temperature is because of the lesser thermal degradation by higher cooking temperature. Also, lesser thixotropic breakdown of the starch molecules during the pacing. But for wrinkle P starch, which has a much higher gelatinization temperature, when we only cook at a 95 degrees Celsius, it cannot be fully gelatinized. When we cook it to 140 degrees Celsius, the starch now can be fully gelatinized. Then when we cool it down, now the well-dispersed amylose molecules, they can reassociate with each other to form a very strong gel network. So after that, we obtain the hydrogel, and then we try to freeze dry it to obtain the cryogel. And then the loading of the curcumin was achieved by using the cryogel and then soak it in the ethanol solution of a curcumin. The reason we use a curcumin here is curcumin is used as a model of the bioactive compounds, and curcumin, they are most of the time present as a crystalline form in water, and they are not easily solubilized in water, and then they have very low bioavailability. So by just soaking it in the ethanol solution of curcumin, we are able to load it into the cryogel. And then, very interestingly, we also determine loading capacity of the curcumin in a different gel. What we observe is, seems like when the cooking temperature increase, actually the loading capacity also increase for both of the starch cryogel. So which means actually the loading capacity is not directly linked to the gel strength of the hydrogel of the starch. So we are looking at the size and also homogeneity of the pores in the cryogel, and also we are very interested in the thickness of the cell wall in the gel. So we hope we can find out the answer why when we cook at a higher temperature, the starch-based gel, the cryogel will have a higher loading capacity. And also we try to compare the system developed by our lab, then compare with other starch encapsulation system for curcumin. And actually you can see these are our samples from the round P and also wrinkle P cryogel. When we compare one paper from 2019, they prepare the wheat starch aerogel. Seems like our gel performed better. And then we'll also compare with some soluble starch nanoparticles. And then they use a different concentration of the gel. When we look at it, we can say our cryogel system, they are either better or comparable to the soluble starch nanoparticles. So this is very exciting results. And what we are doing now is we want to determine the resin profile of the curcumin in the gel. And also we want to determine the, how the resistant starch will affect the resin profile. And lastly, I want to share with one study. Actually, the research was completed by Dr. Malkinson and Dr. Yuqing Liu at the University of Manitoba. They are collaborators in the SI program, but they are at a different university. So for this study, we try to prepare biomedical material, how we can achieve the goal. So for this particular study, we start with the starch. The first step, they did a modification. They want to introduce the carboxy methyl group onto the starch. And then the second one, they want to introduce the methylcrylate group. You can see here. This is a two-step of the modification. Then after we introduce this group to starch molecules, then through the covalent cross-linking, this is a covalent cross-linking step, and then also the calcium, the ionic cross-linking. This one mainly work on the carboxy methyl group. So through the covalent and also ionic double cross-linking, we can develop some very interesting hydrogel for hemostasis use. So this is the gel actually they prepare in their lab. Then this one is without the calcium. So which means it only have the covalent cross-linking, but this is with a different concentration of the calcium. What you can see is with the presence of calcium, actually this kind of hydrogel, they form a better shape, they have a better gel strength as well. And then they also, after they prepare the hydrogel, they also freeze dry the sample to prepare this is a cryogel sponge. They call it a cryogel sponge. And then what you can see is within 1 second, this gel can absorb a really large volume of the liquid. So that's the reason we want to use it for the hemostasis use, right? And then you can see when we only have the covalent cross-linking, it can absorb 70-fold of the liquid. But when we increase the like the calcium to enhance the ionic cross-linking, you can see the water absorption decrease. This is because of better integrity of the cryogel. But because when we use a material for hemostasis use, you want to have a strong water absorption capacity. So we try to only focus on the least gel and also the 0.01 molar of the calcium. So actually, they went ahead to really prepare the hemostasis material, and they test its performance on a mouse tail amputation model. And then what they did is they basically cut the tail of the mouse, and then they apply the material, different type of material to help to stop the bleeding, right? And then for the blank, you can see at the volume of the blood is very high. They also include like the gelatin sponge with a commercial product. They also have this sponge with no calcium and then with the 0.01 molar of the calcium. What we observe is compared with the blank commercial product, and then also this one will give the least blood loss, and also the bleeding time is the shortest. So which means this sponge made from pea starch really show good promise for the hemostasis material. But this modification is mainly achieved by using two modifications. So it's a double cross-linking. That's just one thing I want to share with the audience. So we are getting close to the end. Here are some takeaway messages I want to share with you. Starch is known as a common and abundant polysaccharide. And then the value-added processing of post starches. Actually, we need to build it on the unique functional and nutritional attribute of this type of starch. And also the strong gelling capability of the pea and other pulse starches make them promising for food, nutraceutical, biomedical, and biomedical material applications, as already highlighted in my presentation today. And then the functional property and nutritional quality of the pea and other pulse starches can be further enhanced through physical, chemical, and all enzymatic modification. Actually, in my lab, we try to use a different method to modify starch for wider industrial applications. One last thing I want to emphasize is the physical interaction between starch and protein fiber. As I presented in the pillar 1 fractionation, you can see if we can weaken their interaction, we can enhance the fractionation, right? We can improve the separation of starch and protein. But another very interesting thing I want to emphasize is this kind of interaction also affect the functional and the nutritional profile of the pulse-based ingredient. For example, pulse flours varying in particle size. Because we are running out of time, I'm not going into the paper, but in this paper we published in 2024, we actually review that the coarse particles, which has a compact starch protein fiber matrix, and can really significantly affect the pasting and gelling performance of different pulse flours milled under different using different sieve, and then we determine the pasting properties at different temperature. In the end, I would like to thank the different funding agencies in our province and also in Canada for the financial support for the exciting research. This is a photo of our group and our group members and also our family members. We took the photo in August this year. We went to a provincial park to celebrate the good weather. So that's all about my presentation, and then I'm sorry it took a little bit longer than expected. I'm ready to take any questions you have. Alternatively, you can just send me email. I will reply to your questions. Yep, that's all, and I will stop sharing.
Thank you, Yongfeng, for this comprehensive overview of pulse starches and the latest research in your lab. We will go through a few questions. There are a number of them, and others that are not answered now, you can address them later on, as you mentioned. One of the questions was, what do people use cell wall fiber for?
Sorry,
what do people use cell wall fiber for?
I think most of the time for cell wall fiber, people will further grind it to control the particle size, because it will really affect the functional property of the fiber. And then we can use it, as I mentioned in my presentation, you can add it to bakery goods. You can add it to extruded snacks, for other similar product, to mainly to increase the fiber content of the food products. I think that's the main use. And then what I learned actually from Dr. Mehmet Topik, the president of Saskatchewan Food Center, is he shared with me is actually pet food industry also very interested in using the different cell wall fiber, because sometimes they will also want to increase the dietary fiber content of their product, and we can use it for the same. But I believe the key thing is you need to mill it, you need to further grind it to control the particle size. Then that can affect the performance in the different either human or pet food products.
Thank you. The other question is, could you please let me know how the peak viscosity in RBA would relate to the amylose content?
That's a good question. In a short way, most of the time, if you have a high amylose content, the peak viscosity will be lower. High amylose content, lower peak viscosity. The main reason is because the amylose, particularly if you have some lipid in the starch, for example, like a wheat starch, when they have a good endogenous lipids, then you have amylose endogenous lipids, the presence of this component tend to restrict the swelling of the granules during heating. So because of that, when you have a high amylose content, particularly with the presence of endogenous lipids, they tend to decrease the peak viscosity.
Yes, thank you. And the other question is, what properties differentiate pulse starch from commercial starches and their ability to improve texture of plant-based meat products?
Long, so I will just give me 1 sec.
Yeah.
So I think for the properties, I already summarized on my slide, and also you can refer to the paper regarding the application is, sorry, Puba, is in which meat product?
Yeah, and the ability to improve texture of plant-based meat products.
Or texture of
Yeah, in the texture
plant-based
too.
meat
Yeah.
product. Okay. As far as I know, most of the time when we prepare like a plant-based meat analog from post protein, usually we don't see a significant level of the starch. Because for example, like the isolated, like the either pea or lentil fava bean protein isolate we obtain, most of the time the starch content is very low. It's less than 1 or 2%. So I think in order for the protein to really form that kind of fibrous structure to provide the texture, my understanding is probably starch is not a required component and may even play a negative role based on my understanding of protein and starch chemistry. So, Pete, for the like a plant-based meat analog, I don't think it plays such an important role because most of the time you will see a lower level. But for some of the meat product, when you want to increase the water holding capacity and also to make the product juicier, and you want to, for example, bring down the processing cost, starch can be added at a very low level. I've seen that like 1 or 2% as a binder and a stabilizer. That's in a real meat product. So I hope that answered the question.
Thank you. Do protein starch interactions in pulses reduce nutritional bioavailability?
For starch, it's the interaction. Actually, we have data to show that. We are writing a paper. When the protein and the fiber, they entrap the protein, they entrap the starch granules. Even after cooking, sometimes this kind of structure will be retained. Then they will decrease the starch digestibility for sure. And then in terms of the carbohydrate nutritional value of starch, it's actually considered as a positive thing because it can give you low glycemic response and also can give you more resistant starch. It's a positive thing. But I thought about it in the past few years, how it will affect the bioavailability of the protein. It's a very good question. Actually, we received funding from our federal government last year. We are going to look at how the starch and protein interact during the extrusion processing. We're going to vary the different ratio of the starch and protein. We want to prepare the extruded snack, and then we are going to look at the in vitro and in vivo digestibility of starch and the protein. We will try to do in vivo for protein as well. So hopefully at that time, I will give you more relevant information. But what I'm right now, I don't think I read too much about that regarding how it affect the protein. I don't have very good answer for the protein side, but hopefully future research can lead us to some good directions. Regarding other nutrient, it may affect if for example, like some of the minerals or vitamins, if they're entrapped in a matrix, I believe during the processing, if we don't destroy that kind of structure, they will be retained there and affect the availability. That's how I would like to answer this question.
Thank you. Other questions like Vita fiber sweetener, can starches be used for altering or creating other flavor perception?
So for just 1 second.
Yeah.
Like a Vita fiber can to alter or create a flavor perception. To create flavor perception, starch most of the time is a blend. We already know that, particularly after isolation. But in I was writing a book chapter on starch, the different single helical complex structure. And actually starch, there's some very good study. Starch actually can be used to complex with some flavor compounds. They can be used to control the release of the flavor compounds. But the challenge of this technology is even you can control the release, but after 2 or 3 weeks, and it will be released anyway. So I don't think it's a very effective approach, if that's what you are asking. So my answer to this question is starch will interact with some the flavor compounds to affect the release. Can really some people even they prepare the single helical structure first. Then they will remove the organic solvent, for example, ethanol. Then they will use that to encapsulate the flavor compounds to control the release. There are some good papers from the States, University of Alabama. You can find the papers. Then they can be used to control the release, but most of the time as the encapsulation system is not very effective. I don't think it's as effective as like a cyclodextrin or some other system, but I still believe this area was further exploration because starch is affordable and has a very bland flavor as a raw material and won't really affect the system flavor. But to use a starch itself to provide flavor, I think that's very challenging because starch, particularly after you isolated pork starch, is very bland. I hope that answered the question. If not, I can provide more clarification.
Okay, thank you, Yongfeng. And we'll just take a couple more questions and then we'll just way past our time here. What are the benefits of using pulse starch to replace gelatin or pectin in different applications?
Yeah, I think I share on the slide. Actually, in the industry, people have used it to prepare the different like other ingredient. I think that's because of the strong gelling ability of the pork starch, and I can share with you. We have worked the pork starch from different sources. Very interestingly, they all show better gelling ability than other common starches you can find in the market. And then among all the pork starches, for some reason, fava bean starch always form a stronger gel than pea or lentil. I can use the word always. Usually I don't use this word in scientific work, but at least based on our work, if you use the same concentration, fava bean always form a better gel than pea and lentil. So when we use it to replace the gelatin or pectin, I think one big advantage is the lower cost because starch is a affordable, really abundant polysaccharide we can obtain from different crops. So I think that's one big advantage. And another advantage is for vegan or vegetarian consumers because gelatin is still considered as a like a protein based, animal protein, right? It's a so if you want to prepare the product friendly to vegans or vegetarians, you can use pea starch. It's definitely plant-based, and then also it's non-GMO and gluten-free. Those are some of the benefits I would like to share. But I think low cost and vegan or vegetarian friendly, I believe they are the two main advantages.
Good, thank you. And one last question. Starch has an interesting gelling properties, as you mentioned. Part of your research focus is focused on biomaterials for biomedical application. Given such a gelling characteristics in starch, it can be a great target for drug delivery applications. Have you studied them for such applications?
Yeah, I think yeah, your interest is also our interest. That's reason in the one project in the SI program, we try to use the starch to develop the delivery system for curcumin, right? It's I know it's not a drug, and in my presentation I try to use the word nutraceutical instead of pharmaceutical, because for pharmaceutical use, there will be a lot more work to do. But I agree with you because of the gelling ability, and particularly if we remove the water, we can have the cryogel, and we can even have an aerogel, and then we can even control the gelling process to manipulate the microstructure of the gel. So let's actually, we started a project last year and we already achieved some very interesting results as I presented in my talk. Is, for example, if we control the cooking temperature, their gel strength, their gel microstructure will vary significantly, right? So I think that's a good starting point, but in the future, we want to do more to use a different method to modify the starch and to control the structure of the like the pore starch based gel. And also we want to control we want to enhance the digestibility, want to enhance the resistance of the starch, because one issue I can anticipate in the future is when we try to develop a starch-based delivery system, particularly if we want to deliver the drug to colon, most of the time the starch will be fully or almost fully hydrolyzed in the small intestine, particularly if you work with the native pea starch. If we cook it, we prepare the gel, so it will be highly digestible. Then if that's the case, I think that will be challenging if we want to deliver the drug to certain part of our body. So to answer the question short is, I think that's definitely when we develop a system, I think it can be useful for other drugs with sharing similar physical chemical properties as curcumin. That's one. I think definitely that's our long-term interest. Second thing I want to share with you is we are going to use different methods to control the microstructure of the gel. That's the key. And also to control the digestibility of the starch. Because starch is different from almost all other polysaccharide, it's highly digestible. Once it's hydrolyzed, the matrix structure we built in the beginning, it will be gone. It cannot help you to deliver the drug. It cannot you to encapture the drug. So I think there is more work we need to do, but what I presented here is a good starting point, and hopefully we can share more findings with you at other webinars or conferences.
Thank you, Yongfeng. And I think, yeah, we are way past the time here, and we'll just call to end this webinar. And thank you very much for this insightful presentation, Yongfeng. And I also take this opportunity to thank the audience for their questions, for staying with us. And until next time, goodbye, everybody. Goodbye, Yongfeng.
Yeah, thank you, Huba and Carmen, for all your efforts. Really appreciate it.
Thank you.
Yeah. Talk to you later.
Bye.
Bye.